This paper addresses an important issue. Basically, it's about how extreme precipitation is related to warming. So, global warming is happening. In the mean, warm air temperatures will mean more water holding capacity, which goes by Clausius-Clapeyron. So, 1 degree C warming should give you 7% increase in humidity, and then relative humidity depends on many other things, whether you're on the ocean, land, etc. And global precipitation can be scaled with respect to how the energy balance has to happen. And then there is extreme precipitation. So the mean precipitation and the extreme precipitation are not necessarily related to warming the same way. So this paper wants to address something that is not resolved just by looking for the scaling. And it says thermodynamically inconsistent extreme precipitation sensitivities across continents driven by cloud radiative effects, which means if you just look for a relation between extreme precipitation and temperature, you don't find a uniform scaling or relation between the two across land. But if you take care of the cloud radiative effects, which are not uniform, then you end up getting a positive relation between them, which means as warming happens, extreme precipitation goes up. Okay, so it's a subtle but important point and should help understand how the models are doing it and whether predictions can be improved and so on. Extreme precipitation events are projected to intensify with global warming, threatening ecosystems and amplifying flood risks. However, observation-based estimates of extreme precipitation temperature sensitivities show systematic spatio-temporal variability with predominantly negative sensitivities across warmer regions. So this is the key concept explored here: extreme precipitation temperature relations and how they are sensitive to warming, and the observational records show that they are negative across warmer regions. Here we attribute this variability to confounding cloud radiative effects which cool surfaces during rainfall, introducing covariation between rainfall and temperature beyond temperature's effect on atmospheric moisture holding capacity. So atmosphere is warming, its moisture holding capacity is increasing, then rainfall happens, which is associated with clouds, and that cools the surface, and that's going to add some complications to your calculation of how warming is related to precipitation, extreme precipitation. And they find a way to remove this cloud radiative effect and show that the relation is consistently positive. We remove this effect by using using a thermodynamically constrained surface energy balance and find positive EP to the sensitivities, extreme precipitation temperature sensitivities across continents consistent with theoretical arguments. Median EP-T sensitivities across observations shift from minus 4.9% per degree C warming to 6.1% per degree C in the tropics, and minus 0.5 degree C per degree C to 2.8 degree minus 0.5% per degree C to 2.8% per degree C in mid latitudes. Regional variability in estimated sensitivities is reduced by more than 40% in the tropics and about 30% in mid and high latitudes. Our findings imply that projected intensification of extreme rainfall with temperature is consistent with observations across continents after confounding radiative effect of clouds is accounted for. Okay, so that's the main message, and you can skip the rest of the podcast if you want, but I'll read some text and look at some figures to show how this actually works out. Okay, I don't know why I did this, but nonetheless, extreme precipitation events can lead to catastrophic floods and are expected to intensify with global warming following the increase in atmospheric temperature at the rate of 7% per Kelvin, Clausius-Clapeyron. While the climate models have been largely able to simulate such an increase, observational evidence to validate these changes is challenged by diverging trends and the inhomogeneity of rainfall records. Alternatively, studies test this response in observations by estimating extreme precipitation sensitivities with respect to local near-surface air temperatures, forming an equivalent relationship to Clausius-Clapeyron equation. These so-called extreme precipitation temperature or EPT scaling rates show significant deviations from the Clausius-Clapeyron or CC rate of 70% per Kelvin with systematic zonal variations. EPT scaling shows a monotonic increasing relationship at high latitudes, hook-like structures in mid-latitudes, and a monotonic decreasing EPT relationship in the tropics. Consequently, EPT sensitivities remain largely negative over most of the tropical regions, in contrast to positive changes projected by climate models and observed trends. A number of factors have been argued to cause deviations in the EPT scaling, including shifts in atmospheric dynamics, atmospheric stability, change in rainfall types from stratified to convective, stratiform to convective, rainfall event duration, cooling effect of rain itself, availability of moisture, and saturation deficits at high temperatures. Alternative scaling variables like atmospheric and upper tropospheric air temperatures and moisture indicators such as dew point temperatures and integrated water vapor have been proposed but offer only marginal enhancements in scaling. Using dew point temperatures showed improvements, but it underestimates rainfall depth information. Rainfall depth information fails to fully address negative scaling and peak structures in tropical regions and provides limited insights on rainfall sensitivity to increasing temperatures. As a result, there remain large uncertainties in using present-day scaling to project changes in future precipitation extremes. So you understand what's already warming is happening, already extremes are changing. You want to understand the relation between warming and extremes so that in the future you can interpret them properly for how extremes will change with warming, will continue to change. And many theories have been proposed for explaining the observed relations and spatial variabilities, etc. They are adding another data point. Is this the final answer? Unfortunately, it turns out that it never is. That's why you have so many other ideas before. Here we show that a large part of this uncertainty in EPT scaling can be explained by confounding radiative effect of precipitating clouds on surface temperature as opposed to rainfall effects. Clouds associated with rainfall events significantly alter the local scale energy budget as they reflect shortwave radiation to space while they absorb and re-emit long-wave radiation back to the surface. Consequently, they cause changes in surface temperatures, mostly resulting in a net cooling across warmer regions and periods. This cooling makes observed temperatures co-vary with precipitation and thereby affects the causal nature of precipitation temperature scaling relationship. So if you don't account for this part, then you will assign everything to extreme precipitation and temperature, and you end up with confusing scaling relations. As a result, scaling rates not only show how precipitation changes with temperature, but also reflect how synoptic conditions associated with the rainfall event affect temperature. Primary objective of this study is to quantify to what extent the covariation between clouds and temperatures affects the regional EPT sensitivities. Global mean sensitivities give you some sense of what's happening, but ultimately what happens locally is what is most critical for understanding where we are going at any place. Most negative EPT scaling also occurs over tropical oceans. To investigate the impact of cloud radiative cooling on these scaling estimates, we extend our analysis to include oceans using rainfall temperature data from ERA 5 reanalysis and radiative fluxes from NASA CERES, which is a energy radiation satellite basically. Our energy balance model was able to reproduce surface temperatures across oceans reasonably well. The scaling became positive across the tropical oceans after the cloud effects were removed. These estimates were consistent with what has been reported using dew point temperatures as a scaling variable over oceans. These results confirm that the negative scaling in oceans can be explained in part by cloud radiative effects as well. However, it is to be noted that cooling over the oceans may result from factors like wind-induced upwelling, turbulent mixing, and heat extraction by storms, which remain unaccounted for in our current approach. So, cooling associated with rain and clouds are more complicated over the oceans as opposed to land, so you have to keep that in mind. We found that the number of grids exhibiting sensitivities greater than the Clausius-Clapeyron rate, super CC scaling as it is called, over land increases more than threefold after removing the cloud radiative effects from temperature. Most of this change occurred in the tropics, with regional patterns being consistent across observations as well as ERA 5 reanalysis. The super CC scaling cannot be explained by the thermodynamic constraints on saturation vapor pressure alone and has been attributed to the dynamic factors including enhanced moisture convergence and increased moist updrafts within clouds. These results suggest that the presence of super CC scaling in observed EPT sensitivities is largely underestimated and cloud effects on temperatures are not taken into account. So that's the main point, and we'll just look at some figures to confirm what the text has been saying, that the EPT relation becomes more consistent with what we expect from just pure humidity dependence on temperature and rainfall dependence on humidity. So you're looking at tropics, mid-latitudes and high latitudes in terms of temperatures versus intensity of rainfall in millimeters per day. So you can see it's strongly negative here. Mid-latitudes is much more flat, whereas high latitudes have a slightly positive relation, and you can see scaling rates observed here. There are of course exceptions where you have sensitivities that are positive, and there are regions where sensitivities are negative. So if you look at latitudinal distribution, you see a strong negative over the tropics and flat and maybe slightly positive at high latitudes. Of course, there's large uncertainties as well. So scaling of extreme precipitation with temperature in observations. Global map of extreme precipitation, which is done as a 95th percentile of rainfall observed. Temperature, EPT, sensitivity estimated from quantile regression method. You can follow up on the methods. In B, that's in B, we have zonal variation of estimated EPT sensitivities. That's B. So that's latitude and zonal mean. I don't know why it's called zonal. It should be meridional. Scaling between, scaling curves between daily extreme rainfall intensity and temperature for tropics, mid-latitudes and high latitudes. The light orange lines show the scaling curves for each grid, while the dark orange line shows the mean response of all the grid cells. Black dotted lines indicate the CC rate of 7% per degree C, so you can see how those change. The black dotted lines indicates, okay, so note that logarithmic scale, la. Okay, this is cloud radiative effect, scaling of cloud radiative effects with temperatures. Strong, so this is now looking at net cloud radiative effect in watts per meter squared with temperature. Strong negative, similar in mid latitude, but at high temperatures it begins to slope negative, and high latitudes have positive with some regional variations, and here is the zonal mean meridional variation. What do we do with it? Basically you subtract it, and now you remove the cloud radiative effects that you see here and look at the scaling again, and now you see much more consistent colors, blues everywhere except over very dry regions like the Middle East and Pakistan, Afghanistan and parts of Northeast Africa, and Greenland of course is all ice. And now this latitudinal distribution also largely becomes positive everywhere. So now tropics bend completely the other way. Mid latitudes have a very different behavior as well. If you look at these, right, this is negative to positive, this way to this way, and this gets a bit stronger. Okay, so you can see now intensity in millimeter per day versus temperature, the scalings are quite different. So this is the main idea, and comparing extreme precipitation temperature scaling rates with and without cloud radiative correction across regions and data sets, just to show that even if you used different data sets like CPC and GPCP. So this is scaling rates, residuals, and scaling rates and residuals for CPC and GPCP. It just basically tells you that they are not rainfall data is always a problem. Non-uniformity and lack of time scales, spatial scales to extract extreme precipitation and so on. So we have to just keep that in mind even when we compare observations. But the main story, as I said, is that there have been other explanations before, but the new addition of cloud radiative feedback becoming an issue is something that is new, and of course this will be looked at by others, and we'll have some more papers looking at this issue, I'm sure. Okay, so this is the hook structure here that we will talk about. So I'm jumping a lot of the text and just picking the main points just based on my own sense of what is really salient about this paper. Some nice cute bird that I'm looking at. Our results imply that the hook structures and high temperature thresholds at which the scaling breaks down or negative scaling occurs, also called peak temperatures, will not limit the intensification of extreme rainfall in a future climate. This is consistent with the reported shift in peak temperatures towards warmer and wetter conditions diagnosed using climate model projections. Basically, there are all kinds of issues about threshold temperatures for convection and what happens to that threshold with warming. And here we are talking about shift in peak temperatures towards warmer and wetter conditions according to model projections, but you have to be careful about these because depending on models for these is always a bit tricky. However, the extent to which the modeled shift in peak temperature relates to cloud radiative effects in climate model projections remains a potential area for future research. In other words, if you derive cloud radiative effects based on observations and show that that is confounding your EPT relation, then are the models capturing the same thing, and what it means for the future in model projections. So those are further details that have to be looked at. Our findings can also be extended to address the observed inconsistency between extreme rainfall and stream flow sensitivities to increase in temperature. So that's an additional rainfalls. The catchment area integrates the rain and produces stream flows. This inconsistency has largely been attributed to factors such as rainfall duration and antecedent soil moisture conditions. However, the role of clouds in affecting these differences has not been explored yet. Given that the time of concentration can vary significantly across catchment sizes, the temperatures sampled for rainfall and stream flow extremes may correspond to different radiative conditions influenced by cloud effects, potentially playing a key role in affecting these sensitivities. So this cloud radiative effect impact on extreme precipitation temperature scaling will extend to stream flow scaling as well. Our approach, so I'm just jumping ahead, our approach, which removes the confounding effect of clouds on temperatures, thus provides an efficient tool for diagnosing sensitivities of other hydrological variables beyond rainfall extremes as well. Okay. To conclude, our analysis demonstrates that the observations across global land are consistent with the argued intensification of rainfall extremes with global warming after covariation between clouds and temperature is accounted for. Cloud radiative effects can explain most of the observed variability in the extreme precipitation temperature sensitivities, including negative scaling rates in the tropics and the breakdown in scaling at high temperatures. This resolves the discrepancy between the apparent negative scaling rates in observations and the projected increase in precipitation extremes by climate models. So if you correct the observations for cloud radiative effects, then they become consistent. More work is still needed to understand the existing uncertainties about observed changes in the rainfall dynamics with global warming in order to reliably extrapolate observationally derived EPT sensitivities directly into the future. Our findings further highlight that the rising threat of increased rainfall extremes with global warming across continents is already evident in observations emphasizing the urgent need for more effective strategies for climate adaptation and disaster preparedness. Well, this extension at the end is always obligatory, but you understand that the core concept of removing confounding cloud radiative effects on surface temperature to get a better handle on the extreme precipitation temperature relationship is a cute one, and hopefully more people will test it and see what the models are doing and what it means for projections and so on and so forth. Okay, I say so on and so forth a lot if you noticed. Okay, anyway, let's meet in the next podcast.